Arc length and surface area. So just a couple nice pictures where if you want to find the length of an arc of something, you did arc length last year in pre-calc, but that was S equals R theta. That was only along the length of a circle. This is for any arc whatsoever, right, that the calculus will handle. So if we want to find the length of an arc, just something like that, I gave you an equation, I want to find the length of that curve from there to there, this arc length formula will work for us. Also, what we're going to learn is if you're making like a lampshade, you don't really care about the volume, you care about the surface area, right, of that lampshade right there. So which means that's what we're going to learn, the surface area formula. So we got arc length and surface area in this section. So the arc length formula is the integral of the square root of 1 plus the derivative squared. That's it. So this is a pretty straightforward example here. So you have a function, take the derivative, and then you're going to do your arc length formula. So you're going to integrate it. And they give you the picture in the book there. So you see you're going to go from 0 to 9. You're going to do the square root of 1 plus that derivative squared. So you have an easy integral there, easy u to u, integrate it, plug in the numbers, switch your x's to u's, plug in the numbers, and then get that exact answer right there. So we're going to accept answers like that. Like if you get like 5 to the 3 halves, you could make that 5 radical 5 if you want, or you could just leave it as 5 to the 3 halves as long as we're getting that exact answer. So that's just a pretty easy, just make sure you take a derivative, use the formula. And then here's another arc length example that I squeezed in here. This is about as difficult as these things get with the algebra. The algebra is a little bit nasty sometimes on the surface area and arc length problems. So I just wanted to show you about as difficult as these get. Don't be too alarmed. They don't always get like this, but this is as difficult as they get with some of this stuff there. So if I want to find the arc length of that curve between x equals 1 and x equals 3, the good news is whatever your equation letter is in, that's what kind of problem it is. So if you have y equals x's, it's a dx problem, and these numbers are going to be x's. So just use whatever the equation is going to be. There's not anything crazy that you got to do to figure out what kind of problem it's going to be. Whatever your variable your equation's in, use that as your dx problem on this one. So what I'm going to do when I take the derivative, that's just multiply by the power decrease the power by 1. So I like to rewrite it like that, multiply by the power decrease the power by 1. Now, the moral of this section is to get common denominators one single fractions. We're going to be doing that a lot, okay? So take your derivative, leave the stuff broken up when you take your derivative, but then after you take the derivative, get a common denominator of one single fraction. So put like an x cubed on the top and the bottom there, added up the exponents. Here I already had the 2x cubed, so that just carried over. So take your derivative, leave the stuff broken up so you can use your power rule. After you take the derivative, get a common denominator of one single fraction. You don't want to be plugging into this formula and you're going to be like, what the heck's going on right there? So I want to make sure that you understand where all this stuff is coming from. So when we square root stuff, it's going to be helpful to have that in terms of one single fraction, not like 4 different fractions inside of a square root. And then it's like, what the heck did you do with that? Because sometimes it's going to be impossible to factor and simplify that. So do your derivative, get your one single fraction, then plug it into your arc length formula. So you're going to integrate the square root of 1 plus the derivative squared. And that's the moral here. Like, you can't square root stuff when you got that plus right there. You're going to need to get one single fraction again. So notice what I did. I came over here to the side. I squared the top and the bottom. And then that's where I got that. And then when I had the 1 plus, that's when I got my common denominator is at 4x to the 6 over 4x to the 6. So there's the 1 plus that thing squared. And be careful when you're multiplying it out, you're adding those exponents. You get a 12 right there, not 36. So I squared it, got my one single fraction, which was this. And then I can condense it. Now, typically we give you something that you can sort of work with the algebra right there. If we ever can't, then I'll show you enough way how to do some stuff in the future there. But right now we're going to give you stuff that you can handle, that you can integrate. And so notice that this is all underneath that square root. So you can actually factor this, make that x to 6 plus 1 squared. Because if you multiply it all out, you're going to get that. And then you're going to square root the top and square root the bottom. So when you square root the top, that 2 disappears. When you square root the bottom, you're raising that to the 1/2 power. So you're multiplying those exponents. So you're going to get this 2x cubed. And then pull out the 1/2. Get those extra things out in front of there. And then you have just the x cubed on the bottom. You have a monomial on that bottom, which means you could do a that over that over that problem to simplify it. Then you have an easy integral, plug in the numbers, get that arc length right there. All right, so a little bit messier of a problem there, but please practice that. You got a couple in the homework that are just like that. Model that example, go back and make sure you're trying to do these steps that I'm having you do. Take a derivative, get one single fraction, plug it in there, get another one single fraction, square root the top and bottom, and you typically will get something very easy to integrate right there. So there's your arc length. You could run into those algebra steps on an arc length problem or a surface area problem. The surface area problem, very similar formula. You do have a 2 pi out in front. You do got this, the integral of the square root of 1 plus the derivative squared, but you got this extra r of x in there. Okay, so you got this extra r in there. And it's not to be confused with like your capital or little r with the disk method. All this r stands for is simply the distance from your axis of revolution to your curve. Here's the good news about surface area. I've only ever seen these either about the x-axis or the y-axis. So that's it. So which means your r, if they tell us you're about the x-axis, your r is the distance from the x-axis to your curve. So anytime we measure from the x-axis up, that's always equal to y. And then if they tell us we're about the y-axis, the distance from the y-axis over to the curve is equal to x, and so your r would be equal to x. So then you always start off with that thinking, and then depending on whether it's a dx or a dy prime, you either get to use a single letter or you might have to change it. All right, so let's talk about that again on this example. So we got this equation from 4 to 9 about the x-axis. So you don't have to graph these, but if you did graph it, you got a square root graph from 4 to 9, and we're going to revolve it about the x-axis, creating this like lampshade type of deal, and then we're going to find the surface area of that shape there. Not a volume, we're going to do the surface area. So take the derivative, and then so here's where we got to talk about the r. Okay, that's typically the only issues that we have over this, how to get that r. The r value is simply the distance from your axis of revolution to your curve. So since they told us the axis of revolution is the x-axis, the distance from the x-axis up to the curve, that's one of our 4 big scenarios. Anytime we measure from the x-axis up, that's always equal to y. If this is a dy problem, and again, whether it's a dx or a dy problem is dependent on what type of letter is in that equation. Since that equation has x's in it, that's a dx problem. If I have x equals y, then it's a dy problem. That's it, simple. So I'm going to go from the x-axis up to the curve. The r is equal to y. If this is a dy problem, if that was x equals y, I would get to use the y as a single letter in my actual formula. But since this is a dx problem, because it's in terms of x's, I can't stop it at the y. I would have to do that, substitute what that y is equal to, and we got to change it in terms of x. So there's the r is at 2 radical x. If my axis of revolution had been the y-axis, and I do r's distance from the y-axis over to the curve, I would have gotten r is equal to x. And since that's a dx problem, I get to use the single x right there, not 2 radical x. I get to use the single x right there. So hopefully that kind of helps you. Watch that part again, and then we'll let me know if you got questions. But the 2 pi is part of your formula. We talked about how I had to make that the 2 radical x for the r, and then you do the square root of 1 plus that derivative squared. So when you square that derivative, you're just going to get a 1 over x. And then the moral of this section, when you have square roots inside those integrals, you got to get the one single fraction. So get a common denominator, one single fraction. Then we can square root the top and square root the bottom. Those radical x's will cancel out. I already pulled the 2 out. And then now you have an easy UDU. So integrate that, plug in the numbers. And as much as you get some weird answers there, but that's the exact surface area of that shape there, of that lampshade right there. So just practice that and let me know if you got some questions. And it's just the algebra that gets a little messy sometimes, either that or that r value. Sometimes we get something that's impossible to integrate because we have that r value wrong. So you just got to make sure you get that r value right, practice the algebra. We'll go with arc length and surface area, which is beyond the AP test as well.